also. Lee is a principal engineer at Intel. He's here talking about source flow control for sub-RTT management of network tail latency. Here at Intel, he is in a barefoot switching division. He led advanced applications team in barefoot networks before, producing INT, L4LB, and network tester products on Tofino/P4. At Intel, he's been working on applications across various network data planes, FPGA, SmartNICs, and switch types. He is a co-chair of P4.org applications work group. So welcome, JK.
Thank you, everyone. I'm very happy to talk about one of our latest development on this condition management per se, especially for high performance computing environment. Yeah, this is a collaboration with many members, but particularly with these 3 members actively contributed to the latest development of this technology. Thank you. Next slide, please. So yeah, it's kind of as an attempt to capture what's going on today in high performance networking era. You know, we have InfiniBand, or now it's adaptation to Ethernet, which is RoCE v2. This slide has a number of animations. Just to fast forward, can you just click 5 times? Okay, thank you very much. So yeah, as any other network, we also need congestion control. So the way it works is that, you know, whenever the traffic comes into a kind of choke point, bandwidth congestion point, then that information is somehow carried in the forward direction data packets, either by marking the ECN field in the IP header, or maybe carried as a kind of round trip delay, and is echoed back by the receiver. And finally, the senders came to know about such a congestion either by measuring the delay time through the acknowledgement or timeout or ECN marking. So this end-to-end congestion control is carrying the congestion signal using the forward direction data packets. And we will talk more about this, but one kind of fundamental limitation of this approach is that such a congestion signal itself is coupled with ongoing congestion. So if there's a very high congestion happening in such a queue, let's say the very first packet of such a new flow joining party, then we'll have to experience maybe up to 1 millisecond, depending on your buffer sharing and then queue configurations, to get the congestion signal reflected back by the receiver, and then the senders came to know about that. So it's fundamentally a bit slow. And there are some other limitations we can talk about that. But, and can you click maybe 2 more times? Thank you. So because, you know, end-to-end congestion control is not perfect, the congestion drop can still happen. The RDMA RoCE transport is not really designed to handle packet drops that efficiently because it started from InfiniBand, which is lossless. So in Ethernet, we are using PFC, 8 to the 11, I'm sorry, 8 to the 1 QBB standard. Port flow control pause is basically stopping the upstream port and creating a back pressure towards the sources so that it can avoid packet drops. But as a result, we are effectively slowing down the fabric network. And it also has a number of other side effects, well-known side effects like PFC storm and other operational issues. Okay, so that's basically the combination of end-to-end congestion control, something like a DCQCN used by RoCE v2, together with PFC as a mechanism to avoid congestion drops. But it has some side effects, well-known side effects. Next slide, please. Okay, so here, what we are presenting is something called source flow control. This is the combination of signaling and flow control reaction. The signaling is edge-to-edge L3 signaling. To show that, in fact, can you please click 4 times? Yes, thank you very much. So let's say that this green arrow, the new flow coming from host 1, sender 1, is going through the network and now arrive at this already congested destination top of rack switch, the last hop switch, which is typically the congestion point with large incast. Of course, you can handle other type of congestions, but for the sake of illustration, we are using this incast pattern as the major scenario here. And even before that packet is forwarded to the egress queue, which is highly congested, certain switches, including Tofino, can have a visibility of that congestion information while the packet is still at ingress. So we can have a visibility on the information and make a decision whether we need to react to it or not at ingress, not egress. And using that information, we can actually generate a signaling packet from that last of TOR to the first of TOR switch, top of rack switch. So we call it just SFC signaler. The basic idea is that IP address is reversed so that it can be forwarded towards the source. And then we compute the time needed to drain the congested queue down to a target depth. So we call it pause time. So the time that the senders are better to pause so that the congested queue can go back to the normal status. Of course, we can also carry something like a DACP or any other field in the 5 tuple header so that the congestion point can be correctly identified using those informations. But once the SFC signal is received at the sender, let's say if we have an ideal scenario where the sender host can make use of this information, maybe either tweaking the condition control algorithm or the new queuing system, then we can directly pause that particular flow contributing to the congestion. But we don't want to make that kind of a bit bigger changes at this point. So what you're doing right now is just simply generating PFC. PFC as a sender mechanism provides us very instantaneous reaction time. By the spec, any hardware NIC implementing the PFC mechanism should be able to make that effective reaction on the wire within something like 600 nanoseconds. So with a combination of this SFC signal, which is coming backward from the congested switch to the source switch, here we assume that this typically the reverse direction is not really congested, heavily congested as much as this forward direction queue. And by using something like a PFC as existing flow control mechanism, we can effectively achieve the sub-RTT detection and reaction loop for this ongoing congestion. Then can you click maybe 2 more times? Thank you. Yeah, so we also have a kind of cache table on the first hop TOR switch. So when the SFC signal is received, while it's also generating PFC towards that the initial flow that caused that trigger of this SFC signal, we also remember that information. Let's say the destination IP address and then DACP and what is the kind of pause time required for that congestion point to cool down. And when the second host is sending a traffic toward the same destination or congestion point, we can easily look that up in the table and deem that, oh, this one also needs to be kind of paused. So instead of while the packets are forwarded towards the congestion point, the first hop switch can still generate PFC almost instantaneously without waiting for the first packet of this second flow forwarded all the way to the destination TOR switch and then signal back. So combination of these two has lots of benefits, and then later we can show that we can reduce the kind of application or network tail flow completion time from 2x up to 10x, depending on which workload and the size of the network, etc. So just to clarify, we are not proposing SFC as another lossless network. We aim to detect and react to the congestion as early as possible and protecting the scarce switch buffers resources. But this is not really another attempt to be a complete lossless network. As you can see here, maybe can you click maybe 2 more times, please? Thank you. Yeah, so while this kind of SFC signaling reaction is happening within sub-RTT time, the packets going into this congested queue will be drained and eventually hit the receiver and then act back. So the end-to-end congestion control is still seamlessly working, and a bit kind of longer-term congestion can be still handled by the end-to-end congestion control. In other way, while we are kind of instantly detecting and reacting to this congestion to protect the buffer, switch buffers, the packets already queued up can still carry the congestion information in the forward direction, and then using the acknowledgement, and eventually these the sender side congestion control engines will have information and then react to it to all the multiple RTT time requiring the convergence, etc. So at high level, we believe that we've simulated that this one works together, seamlessly work with the existing end-to-end congestion control schemes. So SFC is not a congestion control scheme, or is not aiming to replace the congestion control. Yeah, and then we are not pausing the switches, so there is no head-of-line blocking happening at all at the fabric. Although in this kind of immediate solution, we are using PFC to pause that particular queue from the source NICs. So there is a small amount of PFC, head-of-line blocking happening at the sender side NICs, but the amount of head-of-line blocking or the effect is less, because compared to blocking the fabric core ports, the number of flows are kind of blocked by this NIC side. Pause is much smaller. And then we do have a number of mechanisms to actually further reduce it down. And because we are mainly targeting in-cast congestion at this point, with that goal, we don't really need to upgrade entire network fabrics. Of course, because we are using PFC, it just works with the standard RDMA NICs or any NICs that supports PFC. Even at the switches, the aggregation or core switches, they don't need to be upgraded as long as they can just forward any L3 header signaling packet. Then we can just upgrade the last hop and first hop top of rack switches and then achieve the same benefit. So you may wonder, what is the format of this signaling packet? Yeah, from Barefoot Intel, we do have a fully programmable switch, which is Tofino. We can easily support any packet header format, whether this is an extension of IP version 6 extension header or kind of new type of signaling packet. So far, we are just using UDP packet and then kind of once designated destination port number to indicate this is SFC signal. But I think this is an opportunity for us, the community and the industry, to come up with now the modern generation of PFC, let's say PFC and then QCN. These are our layer 2 technologies, but now data centers are moving toward the layer 3. So this is probably the time to think about layer 3 congestion signal and then the flow control mechanisms. Next slide, please. Thank you. Yeah, so we briefly touched upon this first question: why not just end-to-end congestion control? Yeah, the link speed is going up, and then RTT time even may goes down because of that. The link speed goes up, and then finishing the same size message. So while the link speed goes up, the packet size or the message size doesn't really go up, maybe go down. So it takes less time to finish the transmission of one particular message or flow. So yeah, the time allowed for the end-to-end condition control to detect and react is actually going down. And then you may wonder why we just not generate something called CNP, congestion notification packet, which is the standard Rocky V2 mechanism from the switches. Yeah, we actually tried it out and implemented it using Tofino P4, but we found that CNP just cuts the rate by half in 1 RTT time. So if you really want to flatten the curve immediately, it takes multiple RTTs. And also, we also found that in some cases, the reaction by the sender NIC upon the reception of CMP packet it's taking sometimes more than 20 microseconds for several regions. Compared to that, yes, PFC reaction time is really short. And then you may ask, what happens if the actual condition drop still happens? Yeah, because we are not completely avoiding condition drops, and then we can do something, many different things. For example, just checking whether this RDMA packets that are being dropped is the last packet or not. Then we may able to apply some different mechanism, like a higher drop threshold on such a just last data packet, so that the normal data packets may be dropped a bit earlier, but the last data packets are the ones that actually create a lot of RTO-based retransmissions, which is the biggest contributor to the end-to-end latency. And we can actually mitigate that using some simple tricks at the switches. Next slide, please. Yeah, SFC. Before talking about SFC, yes, one of the known kind of difficulties in running maybe Rocky PFC was that there are so many parameters to tune, as were mentioned by the previous speaker. So are we adding another set of parameters? Yes, which is just SFC triggering threshold and maybe the drain target, which we need to compute the pause time duration. But just simple configuration like setting all of them same as ECN threshold has proven to be working really well. We also tried many different combinations, but they didn't really make any big difference anyway. Yeah, we talked about the head of line blocking happening at the sender NIC, but it can be minimized potentially by using some multiple hardware queues, because not typically not all the 8 PFC priorities or hardware queues are used for actual X1, X-off priority flow control. So maybe up to 3 of them are used, but not all of them. So we are investigating a possibility to just tweak the software NIC driver so that we can leverage the more number of PFC queues without really impacting the existing QoS and then the priority management. Can you also handle receiver NIC congestion, which was also manifested by the first speaker, Christoph? And we believe so by just maybe letting the NIC to generate PFC towards the last of Tor switch, and at the last of Tor switch, we can react to it by generating SFC, and then eventually just pausing the senders, not pausing the upstream switches. We talk mostly about incast, but you can easily imagine that maybe it's not just incast which may cause this sudden increase of the queue depths. For example, the arrival rate might be the same, but departure rate of the particular queue may go down if there is a higher priority queue and their traffic demand goes up, but then this kind of lower priority queue effective drain rate goes down. But even in that case, because we are just monitoring the queue depths, we can easily detect such case and then react to it. Thank you. Next slide. Yeah, so we tried multiple different evaluations, system evaluations and simulations Tofino 1, Tofino 2, and also different type of simulators. At high level, we have a small testbed with 14 nodes and 2 switches. And also in case of simulations, we tested up to 320 nodes. And at high level, yes, the SFC also worked well with, even with the real applications like a VGG16 machine learning workload. And then we found this performs the best. And yeah, even in the systems, it was able to avoid a head of line blocking in the switches, and such that we are resulting in the small latency and high throughput. And we also compare with not just vanilla Rocky V2 or PFC enabled or disabled, but also we tested against the selective retransmission, which is IRN mechanism published in CCOM 2015 or 16. And when we compared against it, SFC performed much better because SFC avoids drops without any much PFC side effects. But IRN is a mechanism to handle the drops in a more efficient way with the selective retransmission. Yeah, like I mentioned, upgrading all the switch fabric versus upgrading only the Tor switches, enabling SFC at the top of rack switches, basically network edges. We were able to get very ideal performance even when enabling SFC only at the top of rack layer. And you may wonder that how does it work against the longer RTTs, because the SFC signal may have to experience a bit longer signaling delay when the RTT goes up. Yeah, so it has an effect, but because we do have a caching at the first of Tor, we were able to actually react to it, the in-cache surge regardless of the network RTT. Next slide, please. Yeah, this is the last slide. Yeah, this is from simulations with 320 nodes. We compare 5 mechanisms here using Google RPC workload. We have a 50% background traffic on the network load, and then occasionally creating 8% worth of in-cache from multiple senders to one receiver. The in-cache ratio was, I think, 120 to 1. So the 5 mechanisms here, the blue one is go back N, which is the vanilla retransmission mechanism of Rocky V2. So in this case, this is a Rocky V2 without PFC. The orange one is with PFC enabled. And the green one is, instead of using PFC or go back N, we are using a selective retransmission mechanism on the NICs. So it doesn't require any, it doesn't involve any switch side operations. Now the red one is ideal SFC, where all the switches are supporting SFC, and also the NICs are capable of causing a particular flow which is causing the congestion without having any head of line blocking as PFC may incur. And then finally, the purple one is SFC with a NIC side PFC, so which causes a bit more head of line blocking at the NIC. So at high level, the first 3 graphs are showing the application level per message flow completion time and the normalized. So the lower is better. And for different message sizes, then we can see that SFC usually performs better than the other 3. And the purple one is performed pretty close to the ideal SFC, but not always. At the bottom, we are showing the link, receiver side link throughputs, and also buffer occupancy at the switches. And yeah, the SFC with NIC PFC, the more the version that we can enable today still performs better than the other 3, and not as good as something like ideal SFC, but pretty close. Thank you. This is the last slide. I'll be happy to answer some questions.
JK, let's see. I don't have anything here in the chat, so I'm going to open it up to the audience and see if they have any questions. you should be able to, I guess it's a good time to speak instead of typing in. So yeah, go ahead, please. Wait for a minute here.
Okay.
There's one question that came through chat. Do you see this initially only in the Barefoot Intel 810 ecosystem?
I cannot tell whether this type of simple signaling and then conversion to PFC is doable or not in the other platform, switch platform. I don't think this is very complex logic to implement, but at least for now, yes, we do have a confirmation that it works on Topino 1 and 2 from Barefoot Intel. Just generating PFC itself, and then for the NIC side, yeah, it doesn't matter. I mean, actually, the system profile we have, initially we are using Mellanox NICs. It worked because we just need a PFC, nothing other than that. Now, if you want to improve on that, the granularity of the NIC queues that you can pause at the NIC, which may require some of software or maybe some firmware changes. We are exploring definitely on Intel NICs, but hopefully that's also something similarly possible on the other NICs. So short answer today, yes, we have a confirmation on the Barefoot NIC side. It can work with any other NICs. And maybe software changes is possible across different NICs too, hopefully.
Okay, thank you.
Thank you.
Other questions, thoughts, comments? All right, with that, I'm going to say thanks to Jeongkeun Lee for being here and going through the Barefoot Networks application here. So JK, thank you very much.
Thank you very much.